Today we're going to talk about the last way you can do some multiplication in terms of vectors, and to kind of set you up for it and to review the highlights of what we've done, let's go back and look at the two things we have talked about already. We're in section 14.4, but going back to previous sections, we looked at the following things. If you have a vector, and we'll assume it's in 3 dimensions, then you can talk about scalar multiplication. This is going to be indicated by a scalar, which is a number, some kind of real number, times v. In terms of geometry, this is a vector It's a vector, and if you want to specify a vector, you have to specify its direction and its magnitude. It's of length, the absolute value of c, times the length of the original vector. And it has a direction parallel to v. CV will be parallel to v. More specifically, it'll have the same direction if and only if the constant c is non-negative. So CV is a vector of a specified length and a specified direction. And as I've said before, we're going to look at these vectors in 2 aspects. This is the geometrical part, kind of lengthy, but that's what you'll find in your book. Or if you look at it in terms of algebra, in terms of our representation up there, this will be CV1I plus CV2J plus CV3 times K. And that's the algebraic formulation. That's the way you actually compute vectors. Okay, and as I've said before, basically what CV does is change length and direction, possibly. I mean, it's not necessary that you change the direction, but that's what you use scalar multiplication for. Basically change the length, shrink it, stretch it, or perhaps flip it around. And there's an important application of scalar multiplication. For example, let's draw our picture now. If you have a vector in 3 space, let's say it's v looking like this, then one important thing that we have to come up with every so often is a unit vector in the same direction as v. And as we've discovered, you can get that by multiplying the reciprocal of the length of v times the vector v. So there's an important application of scalar multiplication. It allows you to shrink a vector to a unit length, and every so often we have to do that, in fact. Okay, so there was one kind of multiplication. Another kind that we talked about involved 2 vectors. Let's put that picture up. Couple of vectors out here in 3 space, and what we investigated was something called the scalar or dot product. Okay, it's designated like this with a dot between the 2 vectors, and this thing is a number. or what we call a scalar. That's why it's called the scalar product. So when you dot two vectors, you get a number out of the thing. It's equal to, I guess in terms of geometry, this is what we wrote down before. You take the length of v times the length of w times the cosine of the angle in between them, and that's within the plane of the two vectors. So theta, in some three-dimensional sense, is the measure between the two vectors. So that's about all I can do for you for geometry now. There's what it is in terms of the geometry of the problem. In terms of the algebra, if w has the usual representation, this would be the sum of products of the components in the three directions. Okay, and that would be the algebraic formulation for dot product. And we've just last time talked about a few problems involving dot products. We computed a few, and we did a few of your exercises in the book. There are a couple of important ideas tied in with this. One is the notion that two vectors are perpendicular if and only if their dot product is 0. I'll write it this way, borrowing a symbol from your plane geometry class. Two vectors are perpendicular or orthogonal if their dot product is 0. And that's easy to see, I guess, from the geometrical definition. If they're orthogonal, theta is pi over 2, cosine is 0, dot product is 0, and vice versa. So that's a fairly important result. We'll use that a few times as well, a little bit later on in the course. And there was another notion, which I'll again sketch in terms of a picture over here. Let's look into the plane of v and w. So in some sense, we're looking down on that sketch up above. Here is the angle theta. In this case, it's acute. And we talked about one object, which is what we labeled the component of v on w. And that's a number. The component is always a value. When I use that word, it's a scalar, let's say. And we found that that is, in terms of trigonometry anyway, the hypotenuse, which is the length of v, times the cosine of the angle in between. Okay, so that's from trigonometry. That length of that leg of this right triangle is the length of v, that's this distance up here, positive distance, times the cosine of the angle in between. We then said, hey, that looks a little bit like a dot product, and eventually said, well, this is v dotted with w over its length. So a couple of steps later, we found that that was true. And that's well worth remembering. When you want the component of one vector in another direction, you can easily do it with a dot product. And one way to remember it is that if I want to basically find the shadow of v on w, then I dot v with a unit vector in w's direction. So again, here comes that scalar multiplication idea that we were just talking about. Now, your book, I don't think, goes on at this point, at least from what I've seen. Let me throw in a bit more for you, because I think it's time that you saw it. In your physics applications in particular, and sometimes in some of our math problems here shortly, we'll not want just the length of that line segment, so to speak, but what we'll really want is that vector. We want to project v onto w. Okay, and that vector, for better notation, I don't know, maybe there is some, I'll indicate this way. Projection of v onto w is that vector you're staring at right there. Now, what do you need to know for a vector? Well, I'll just set it for the second dozenth time probably. You need to know the direction. Well, that's in the direction of w. And you need to know the length. There it is. That's the component that we just talked about. So that projection that I have there I can do with both the things we're talking about. Scalar multiplication, because here's its length. There's the length of the vector, times a unit vector in W's direction. Again, scalar multiplication. Okay, see what we're doing? And this is pretty typical for vectors. We know what direction we want. We know what magnitude it should be. Use a unit vector, multiply it by that length, and you have yourself the projection. So here, again, is a scalar with the right direction times a unit vector. I shouldn't say right direction. A scalar with the right value times a unit vector, scalar multiplication. Again, what I'm saying is I'll take a unit vector back here. This would be W divided by its length. There's a unit vector in W's direction, and then I expand it out to the size that I want. And I've told you that you should probably do that in your homework as well. The one you just got back, in fact, says, give me a vector in the direction of W which is 6 units long. Well, first make a unit vector, I claim, is the easy way to do it, and multiply that by 6, and you've got the right distance. By the way, there's a little bit of a misunderstanding. There's that problem I just said, find a vector of length 6 in direction of W. There's another problem which says find a vector 6 times longer than W. And so that is just 6 times W itself. 6 times W stretches it out by a factor of 6. So anyway, again, you get the blue vector, which is this, expand it by this length here, and you've got the red vector, the projection. Now, I don't want to leave it at that. I mean, it's easy to write that down, but what do you really have when you sling all the ingredients together? For example, this component that we just saw from over here turns out to be V dotted with W divided by length W. That's the component, and this is W again divided by its length. So here's your scalar times your vector. And if you mush things up a bit, I've run out of room basically, but let me just get to the final step. What you'll finally end up with is V dot W divided by W dotted with W, all times W. And maybe I'll put that in red because that's our projection vector right there. If you need to find the projection of one vector onto another, V onto W, you basically can plug it into that formula. Now that's a bit much to remember, but what I want to do is show you that these dot products and these scalar products aren't as trivial as maybe they first appear. Because you think of it again, I've got these two vectors out here in 3 space. It's really physically impossible for you to basically adjust your vision, your line of sight to see what's going on. How do you get this vector down here? Well, as I've said, with these algebraic ways of manipulating these dot and scalar products, this is a very simple thing to compute, and it's going to be a very important object in lots of your applications later on. This course, Calc 3, physics, and what have you, because you often need to have that vector in that direction right there. So those were the highlights. Again, it seems fairly abstract, but if you remember, dot products, scalar products are pretty easy to compute. It's really a lot easier than it might seem from what you see here at the blackboard. So far, all review. Okay, let's start now with our new section, 14.4. What we're going to talk about is the last thing. This is called the vector product. Let me run those names by you again. We had scalar multiplication. We had scalar product, which is a dot product. We now have a vector product, which is also called the cross product. And really, it's the vector product that you would pair up with the dot product. Those are the two that we're interested in. Okay, here it is. This is why it's called the cross product, because they use a little cross right there. And what you get this time is a vector. So you got to keep that in mind. Dot product gives you a scalar. We always had a number over here with some nice geometrical interpretations, but now we're going to come up with a vector. Well, where do you get the vector? What is it going to be? The two things you need for the geometry is the magnitude. This thing will have magnitude, strangely it may seem at this point, but you'll appreciate it a bit more later on. The length of V, length of W, I'm afraid it's not what it was for the dot product. It's the sine of the angle in between. So here's your vector. It has this magnitude. So far, so good. And what's the direction? Okay, this is why we need 3D. Pretty much everything I've done up until now has been within the plane of the vectors involved. Remember, we had two vectors pointing out in their plane. You can add them, subtract them, scalar multiplication. Everything stays within the plane of the two vectors. That's not the case here. This particular cross product vector, in fact, points out perpendicular from that plane. So the two things you need for this vector are given there pretty well, and not completely though. Magnitude, okay, just take it for what it is. Direction, perpendicular to both V and W. Let me add a little bit more. This is not going to mean much right now, but you'll see what happens shortly in the right-hand sense. So that perpendicularity is in so-called right-hand sense. Well, let me at least pause before we get into the algebra. Let's actually take a look at what this geometry is about. In particular, let's look at a couple of simple cases. I think the simplest would be the unit vectors themselves. What happens to them when you do some so-called cross products? Okay. Okay, let's see. What would I cross J be for my geometrical definition here? Has magnitude, length of I, length of J, sine of the angle in between. Okay, what are the lengths of I and J? 1, those are unit vectors already. And the angle between I and J is 90 degrees, so the sine is 1. So when I cross I with J, I get a vector with magnitude equal to 1.
So how
Question.
do you get the length again on I and J?
Those are unit vectors, always, in the x, y, and z directions. I, j, and k are always unit vectors, and they're all perpendicular. So that's why you get sine of theta equals 1. Okay, the magnitude's no problem. What do I mean by perpendicular to both in the right-hand sense? Well, if it's perpendicular to both, obviously it's perpendicular to the xy plane. That's probably the best way to think of it. The cross product is perpendicular to the plane of the two vectors. But now you have a choice, because you could either have perpendicular up or you could have perpendicular down. There are two perpendicular unit vectors, anyway, of interest. Well, this right-hand sense says that I cross J is a perpendicular vector in the direction of K of unit length. Therefore, it's K itself. I cross j is k. Okay, here comes the right-hand sense. And it's just like the right-hand sense we talked about before. If I cross I followed by j, I put my hand along the first vector, my right hand along the first vector, swing my fingers into the j position, and my thumb points in the direction of the cross product. So I cross j is a unit vector in the k direction, therefore it's k itself. Okay? Let's do a couple more just to get warmed up to the topic. How about j cross I?
Oh, go the other way.
It has to go the other way, right. It's going to be minus k. You start out with j first, swing your fingers around to I, your right hand thumb's pointing downward. Unit vector, that would have to be negative k. So as I think I kind of warned you, cross product is not, maybe I didn't warn you, but anyway, cross product, regardless, is not a commutative multiplication. I cross j is not equal to j cross I. And generally, v cross w will not be w cross v. You might put that down and box that in. It's not really any advantage. I'm just warning you that if you've done one of these problems, you're going to have to almost do it over again. But that's not the case. What was the difference up here was just a matter of direction. You go either in one direction or you go the opposite direction. So what is true is that this is the negative of w cross v. You know, obviously, you just change the direction around. The magnitude will remain the same. So the picture you should at least imagine in 3 space might look something like this. Here is your, say, v vector. Let's assume back behind it, and this is hard for me to try to express to you, but behind it somewhere is the w vector. And with a right-handed system, this would be v cross w. And w cross v would point the other way with the same magnitude down there somewhere. But the important thing is that, of course, this vector is perpendicular to both vectors or to the plane of the 2 vectors. I keep using the word plane as if you were familiar with it. Maybe you are in terms of Euclidean geometry, but we haven't tackled planes or surfaces in terms of analytical geometry, and in fact we're going to use vectors to do that. So that's partly the reason that we need cross product, but you'll find out again, sounds like a broken record, but in physics you'll be using cross products an awful lot. Question?
So will you be using a left-hand sense then?
Not in this class. We'll never use a left-handed sense. I've never seen one yet that isn't right-handed. Class, that is. Yes?
Go again, how, like j cross I is
Okay, j cross I, question is, how did I get that? Well, for one thing, I could go through this thing again, but that's the same. You see, the length is commutative. So it's a unit vector that's either pointing up or down. In a right-hand sense, I start with my fingers along j, swing into the I position, and my right thumb points in the cross product direction. So it's a unit vector pointing downward, has to be minus k. Same thing over here. I'm assuming my w is back behind v some sense. Takes a contortionist, but you swing w out to v, and your thumb points downward. So w cross v is a downward vector. Best I can do it. Okay, let's run through real quick. What do you think j cross k is? It's I. It will be a unit vector. And k cross I will be j, I cross k, negative j, etc. So if you know all those interrelationships, then basically I could give you an algebraic definition of what cross product should be. In other words, I can take v cross w, assume the distributive law holds, and then I'd have v1, v2, I cross I, V1 W2 I cross J. In other words, you'll have 9 entities there that you'll have to worry about. By the way, there's one thing I didn't mention. What, for example, is I cross I? 0. Why? Because they're not going anywhere. Maybe that's what I should say. Anyway, looking at it this way, the magnitude would be 0 because the sign is 0. So if you cross a vector with itself, you get the 0 vector. Don't forget that. J cross J, or V cross V in general, will be a 0 vector. Now, is there any problem with that? Not really. Remember, I mentioned that the 0 vector points in all directions, so it's perpendicular to your 2 vectors. No problem. 0 is perpendicular to both I and I. So it seems to fit into that general classification. Okay, I think what I need to do is, again, before I forget it, is to give you something that is positive. Remember, we had this interpretation for the dot product. V dot W is 0 if and only if the vectors were perpendicular. What I'd like to do is entertain you with this notion. What happens if the cross product is the 0 vector? Well, we just saw a case of that. I cross I is a 0 vector. Okay, one guess was V and W are equal. Not necessarily. I cross 2I would also be 0, as it turns out. Same direction as in the next guess. How about I cross minus I? What would that be? Well, the angle is pi between I and its negation. The angle is pi, so the sign will be 0, and you'll still get the 0 vector. So if it's either the same direction or the opposite direction, really the lengths make no difference, you get a 0 vector, and it really works both ways. This says that the 2 vectors are, again, borrowing some notation from plane geometry, the 2 vectors are parallel. Not necessarily in the same direction, but parallel, same or opposite direction. And that's a nice little fact to use. And we'll come back to that as we need it. I think I've almost milked everything I can get out of it, at least that's apparent. There's another thing that will come up a little bit later. But the real problem will be, as you look at your homework problems, they'll give you a couple of vectors and say, well, what is the cross product? And now you're a little bit stumped, because this isn't going to help you a whole lot. Because basically this says you've got to climb out there in that 3-dimensional picture and somehow measure the angle in between the vectors and figure out which way that cross product goes. Of course, that's ridiculous. But knowing what this is, we still need to know how one computes it in an efficient fashion. Unfortunately, there is no efficient fashion. I'm going to have to give you a little bit of a side lecture, so to speak, to get the definition that your book has. So again, put it on hold for now. How to compute cross products is coming in about 5-10 minutes. We'll see how it goes. What has to be done is talk about something that maybe some of you have heard about. I can't assume everybody has. These are the things called determinants. I was amazed in my other section. I brought this up. Some students said, well, a determinant is a function of a matrix. I hadn't expected that. That is actually true, but that's a fairly advanced look at what it is. As far as we're concerned, determinants are just numbers. Okay, and let me give you an example. In fact, you can give me an example. I need 4 integers, positive or negative. 3? Ms. Miller? Mr. Jake? 4? And Mr. Hushauer? 2. Okay, this is what you call a 2 by 2 determinant. And it is nothing but a number. It's written in this form, kind of an unwieldy looking form. Doesn't look like a number. But the trick that you learn, if you've learned it, is you take this particular cross product, this, I shouldn't say cross now, diagonal product, I guess. You take the upper left-hand number times the lower right-hand number, and then you subtract the product going the other way. Lower left hand times upper right hand. And that's all there is to a 2 by 2 determinant. And I hope that if you've seen one of them, you've seen enough. Turns out this number, this determinant, is 14. How many have seen it, just for my own curiosity? Okay, about half of you. Now you can get into very large determinants. In fact, if you need to solve large systems of equations, sometimes they teach so-called Cramer's rule using determinants. That is not an efficient way to do things. I've heard somewhere that if you do a 20 by 20 system of equations not too efficiently with determinants, it can take you millions of years on the world's fastest computer. That's just a 20 by 20 system. So it's not a real great device for big problems. Fortunately, our problems get no larger than 3 by 3. Okay, so let's talk about what that would be, a 3 by 3 determinant. Well, it would be something with 9 entries. I'm going to let you fill those in. But that, once you have those 9 entries, is going to take more board space than I have right there. So I guess I better back up and get a running start at this thing. Who's going to volunteer all 9 numbers? I need somebody who can get me some quick numbers here. Mr. Toshar.
6, 5, 4, 3, 2, 7, 8.
How about a negative?
Negative 3, negative 5.
Okay, a couple negatives right there. Okay, there's your 3 by 3 determinant. It has to be square. It is a number. Question is, what number is it? Now, this has to be a quick and dirty lecture because we aren't really going to get into determinants other than using mesomnemonic. We aren't even going to compute determinants themselves. What we need to know is what you call expansion along the first row. That's all you need to know for this course. And what that means is that you break this up into 3 2 by 2 determinants. And the way it's done is as follows. You take the first entry up here in the left-hand corner again, 6, and you multiply it by something which has a fancy name called cofactor or signed minor. And that's what you get when you cross out 6th row and the 6th column. You cross out the first row and the first column. What's left over is a 2 by 2 determinant. At least that's what you're supposed to imagine there. And that's what you multiply 6 by. Okay, that's the first step. There are 2 more to go. We go to the next number, 5. We plant a negative sign in front. Don't anybody miss this. Negative, as opposed to a positive that we started out with. Negative 5 times its so-called cofactor. If I cross out the 5 row and column, I'm left with 3, 7, 8, and minus 5. Okay, again, I take the entry, cross out its row and column, and you get 4 numbers left over, and that is the minor that we're going to deal with. And lastly, we go back to a plus sign, a plus 4 times its minor, which is 3, 2, 8, and minus 3. Okay, can you see the pattern? Go across the top row, cross out rows and columns, put the right plus and minus signs in, and that is a way to evaluate this determinant. Now, a word of warning, I know some of you have learned a fancy way of copying the determinant over and doing 3 diagonal products and subtracting another 3 diagonal. That doesn't really work for what we need it for. So if you've seen that one, you better learn this one because this is the way we have to use it. Now that we're this far, let's figure out what's going on here. Again, as 2 by 2s, this is 6 times a minus 10 plus 21. It's a minus 10 minus a minus 21 minus 5 times minus 15 minus 15 again plus 4 times minus 9 minus 16. So what do we get? We get What was the question here? Oh, yeah, 56. Thank you. 7 times 8. That was close. Well, we have 11 here, so that's 66. This is plus 5 times 71, 355. And that's a negative 25 times 4 minus 100. Check me on it. So it's 255 plus 66. That's 321. We in agreement? Okay, a few nodding heads out there. I hope that's a positive response. So that 3 by 3 determinant has that particular number over there associated with it. Well, we have time. Let's finish off what I wanted to do today at least. And that is give you the algebraic way to evaluate a vector using this notion of determinant. And it really isn't a determinant that we use, it's more of a mnemonic. What you do is you write down what looks like a determinant, but instead in the first row you put I, J, and K. If you're going to cross V with W, then you put the first vector's components in the second row. Then you put the second vector's components in the last row. Okay, now obviously if I cross W with V, I interchange the two rows. And as it turns out, that changes the sign of this particular value, which we already investigated. If you interchange the order, you negate the product, the vector product. So someone give me, well, we could use these right here. Let's take this one right here. I'm going to assume those numbers Mr. Ushauer gave me actually represent the components of a couple of vectors. So I'll just recopy those down. What I'm looking at now would be, for example, 3i plus 2j plus 7k crossed with 8i minus 3j minus 5k. This is just what we needed. We have to have some efficient way to compute cross products. So that will be, this will be, if you expand it along the first row, a plus I times its so-called minor minus j times its minor plus k times its minor. Now, unfortunately, I erased it. I'm stupid to do that. Those are exactly the same minors we had before. Maybe someone could read those off so I can avoid doing this.
11, negative 71, negative 25.
Is that what we got? Minus 10. See, that was minus 10 plus 21, right. Minus 15 plus 56. 9 minus 9 minus 10. No, that's not right. I copied the wrong numbers. I did. 3, 2, no. No, we're not in complete agreement, I think. Yes, okay, minus 9 minus 16, fine. So there's your cross product. And there's a big gap here. I have not at all tried to show you that, in fact, this agrees with my geometry. The book does a pretty good job of it. Not perfect, but pretty good. Real big gap. I think there's about a page or two of proof that what I'm doing over here actually produces the vector I told you about over here. I don't have time for that, fortunately. It does work. So next time, we'll pull out a bunch of problems for you, and we'll see how these vector products are used. We'll see you then.